Okay, well...
I'll ring, should I ring the bell?
No.
No?
Ring the bell, go on. You've got to ring the bell. Well, welcome to the AES Melbourne Section June meeting. My name is Graham Huon, and we want to thank Collards here for their support to the section in making the venue and the services available. Tonight we are very privileged to hear from Dr. Anton Hasell on the topic of the specialist bell design process. As a well-qualified sculptor of note living in central Victoria, Anton explores the use of both traditional and digital tools in the design of bells, interactive public space installations, sculptures and other graphic arts. Anton has combined his creative artistic skills with an understanding of how humans hear and the essential elements of metallurgy to create unique bells of many sizes. Anton is well known for the creation of the Federation Bells Carillon in Melbourne and for other public space artworks in Australia and overseas. Anton will probably tell you tonight that he's recently completed the design, casting and tuning of 10 different tone bells for the long now 10,000 year clock project in Texas, USA. I'm sure you'll tell them about that.
I'll try to remember to do that.
Yeah, I'll remind you. Tonight, Anton will briefly outline human hearing and perception as it applies to tone generation instruments. In particular, he'll summarise his pioneering mastery of overtone tuning and difference tone bell design, showing the benefit this provides for all bells, large and small. Anton will then explain his specialist bell design process, from concept through shape design, not giving away too many trade secrets though, I hope, tooling and casting to tuning and the final product. He will show us some examples of his installations around the world, and the presentation will include physical, hands-on examples as demonstrations of his craft. I would like you all to make Anton feel welcome.
Thank you. Okay, so Graham, thank you.
Anton.
Thank you very much for inviting me along. I'm not certain how audio engineers are going to respond to bells, but anyway, it'll be a diversion for you. Esoteric as bells are. Nevertheless, bells have a wonderful, wonderful and important history in civilization, both in Asia and Europe, and I'm really enjoying the process of exploring new musical sounds with new bell profiles. So I started when I was teaching at the Victorian College of the Arts in sculpture. My sculptures were landscapes. As on the picture on the left, you can see a bronze landscape of an island in the middle of an ocean, and then I made some small ones in the early 1990s where I put a clapper inside, because they started looking bell-like. And then in 1995, the Vision Australia was celebrating its centenary, and so they put a brief out for a sculpture to go in King's Domain to celebrate the centenary of Vision Australia. And because I was working on bells, I thought, well, why don't I make 3 bells, bronze bells on a bronze post with a bronze bell base, which you can see in the picture there, and put 3 movement sensors in the base so that people who are blind, who are walking by the sculpture, will activate little strikers inside the bells. And so that began, I won that commission, and that began working with Neil McLaughlin and other amazing people interested in acoustics on the design of bells. Being commissioned to co-create the Federation Bells in Melbourne as part of the Melbourne Festival, International Festival celebrations of Australian Federation in 2001, meant that we were invited basically to design a carillon of new computer-designed bells and a set of harmonic bells, should we invent them, for the Melbourne Symphony Orchestra, and 60 sets of harmonic handbells for that Melbourne Museum holds and hands out to the community for community use. So the design of the bells is all finite element analysis based, and you can see here how the flexing of a three-dimensional object takes place, and each of those flexes generates a frequency. And a bell, a harmonic bell, needs to have a harmonic array of those frequencies in order to sound clearly a single pitch. A European church bell has two notes in it. They're polytonal. The thickening of the bow bow, the thickening of the lip, generates a frequency that is called the foreign note in a European bell, and that's a minor third to its lowest fundamental note. And so every European bell is polytonal, and bell makers from the 18th century onward were trying to design harmonic bells, perfectly musical bells, and that only happened when we applied finite element software to bell design and generated the world's first harmonic bells. This is one of the little Federation handbells, and there's a set of 24 to make 2 octaves in a set of them, and it generates a harmonic array of frequencies to give a perfect pitch, or the best clarity any bell can generate in pitch. So the design of the bell is generated in the computer. A virtual model is then set targets, frequency targets, and the computer optimizes, finds profiles that move towards those targets. When the computer is unable to resolve any further and starts moving away from the targets, it stops, and you have to change the model in order for it to, and run it again, and through a process of iteration it finds a profile, and you can see some complex profiles here that predicts that an actual bell will have a certain sound to it. Now, the red drawing there is a difference tone bell, and that was a computer production or prediction for a difference tone, but so that shape was 3D printed in plastic exactly, and then put into a foundry pattern, and two foundry molds pulled apart, the pattern taken out, put together, bronze poured in, and when the bell was struck, it didn't generate a difference tone. And so it's a prediction rather than a perfect outcome. But nevertheless, without software like this, it's impossible to get into the really complex possibilities of bells. It gets you into the ballpark.
Anton, I don't know, you've got a harmonic series with that bell that makes it sweet. Have you got any here that don't have that harmonic series, or did you bring all your harmonic bells?
I could have brought a little European bell along.
Yeah, so they could hear the clang instead of the sweet.
Yeah, but it was heavy enough to bring just these. So I thought, oh look, you'll know the sound. Often when you're listening on a TV program, you'll hear bells. You know, that program about the village where people get murdered. They often have bells ringing. In England, what is that called? Midsummer Murders. And often you'll hear bells, and then you'll go, oh my God, listen to that awful cacophony of those very old bells, and often I'm invited to look at old European bells, and there's until 1900 they had no control over the tuning of the bells. The Dutch in 1633, the Hemeny brothers, they produced a tuned European bell, but then that secret was lost, and often you get 1890s, 1880s bells that might be a C, you cast on it, but there's no way of defining what the note is. So I haven't got an example.
No, that's okay. They'll all have to go out and research a bell and make a claim.
Yeah.
They'll remember this one.
So the Federation Bells project was fantastic, a fantastic project to celebrate Australia's federation. This is part of Victoria's contribution to Australian states celebrating the Federation of Australia. And so we were invited to build a carillon in Birrarungmar Park of new design bells. Most of them are harmonic bells. When that was invented, we invented that. And then we started getting really playful, and I haven't brought samples of those along. With a European bell, it's a harmonic series with a minor third in that series. And then we had a harmonic bell is often conical. So once we had a harmonic bell, it was possible to say, what will happen to a harmonic bell if we put a minor third in there? So we've got a conic European sounding bell. What if we put a augmented fourth in that bell? So we just set up a frequency series, and the computer program generated profiles for these extraordinary bells that have never existed before, with extraordinary sounds. So the Federation bells have a number of experimental bells, including a 3-tone bell, which is my favourite of all the bells at the Federation bells, and it's the most complex looking one. So it was an opportunity to be very playful about bell design by creating our own new sound possibilities. There's a picture of the 3-tone bell suspended at left-hand side bottom. You can see the complex shape of that bell. These bells were cast using resin sand. Above that picture, you'll see the mould of that bell, and the shapes are given by strickle boards, laser cut steel panels put into a frame and turned on resin sand before it sets. So you turn a shape up, and then the sand sets hard like a rock, and that creates the mould. You do an outside and inside shape, put the moulds together, pour the metal in, and out comes the bell. You can see the pouring of the metal. In 2006, an American sent me an email saying, I want a Japanese bell. And I said, I've been to Kyoto to watch a 1-ton Japanese bell being cast, and I could put him in contact with the Japanese bell foundry. I want writing all over, his name and dates and all sorts of stuff on it. Then I could go to Japan, and I could work with the Japanese bell founders, and I could hammer in the English information into the Japanese moulds, film the bell being cast, do a sound analysis of the bell. You pay me for doing that. You pay the Japanese. They'll send you the bell. I could do it. I could just do it. Oh, you just do it. Okay. I really want to go to Japan and work with the Japanese. Okay. And so this is a 500 kilogram Japanese style bell, and you can see the mould being prepared there. So, so a bell maker is open for every opportunity that they can get.
Anton, can you just take us through the steps that you're showing there?
You can see underneath the drawing of the bell and the profile, you can see the profile. So Japanese bells are really thin and then thickened down at the lip of the bell. So the shape in the middle or next to those drawings, that's the core of the bell. That's the inside of the bell. And the rings where there's information, there's writing. Yeah, the rings, these rings, they sit on top of the core, leaving a gap, which there you can see the gap here. And so they're in units that sit on top of a single core, and they're carefully lowered and put together. And that's in Japan how the bells are made as well. Except we use resin sand. They use a kind of clay that's malleable. So the clay, you can hammer into, and then they lower them down, tie them together, pour the bronze in. And we use resin sand. So and then the bell was cast, and the American said, "Oh, okay, I want it now." So he flew it at some great expense to New York State and his property, where it's quietly ringing away still. Then in 2014, I got these emails asking questions about how long will bronze last for. Well, people are still finding 5,000-year-old bronzes that seem in good condition or reasonable condition. So bronze should last a long time. So every time I got a question from America, I just go answer it in a very straightforward way. And then I was asked, well, would it be possible to make a difference tone bell? And then they explained to me that they were building a 10,000-year clock inside a mountain they were going to hollow out. And Brian Eno who was a member of the foundation, the Long Now Foundation, had worked out a musical scale for the resonance of the hole that they dug out. When I was in San Francisco, they showed me a video of him standing on top of the hole going doo doo to try and get a sense of the resonance of the hole, and from that he developed a musical scale of the bells to go in. And the lowest was C 130 hertz, which is a very large European bell. And so their problem was getting a bell that was 130 hertz, but it was small enough to fit into their space. And a difference tone, organs, to get a C65 hertz note in an organ, you need a 64-foot long pipe. Very few organs have room for 64-foot pipes. The Melbourne Town Hall organ has, I think, 10 32-foot pipes. But they play a 32-foot pipe with its perfect fifth simultaneously, and it generates a difference tone in the audience ear, an octave below the 32-foot pipe. So the audience hears, psychoacoustically, hears the note C65. And so the Americans want to know, was it possible to make a bell that would do that? And so working with a finite element engineer, Ryan Adams, we generated a profile. And as I said before, when that was cast, it didn't sound a difference tone. So I boxed it up. I cast a 316 stainless steel harmonic bell, boxed it up with it, and sent it off to America saying, well, here's the computer prediction, here's the actual casting, it's not a difference tone. Maybe the answer is stainless steel, harmonic bells. So I flew over there, had an afternoon arguing about it, me saying stainless steel, harmonic bell, way to go. They said, we'll let you know. I came back here and they said, keep working on the difference tone bell. So I cast 3 of them and then proceeded to destroy 2 of them, but in the process taking a frequency map. So every time I took a fraction of metal off, I would see how the ratios between the frequencies moved, and then I just continually did that until a bell was untunable, get another bell, and then use what I'd learned from there and take metal off, and destroy that bell. And on the 3rd bell, I managed to use that map to generate a difference tone when you struck the bell. Hallelujah! The sound file went off, and they commissioned me to make the 10 bells. So they were made here in Victoria, and you can see that's the hole the clock is in, with a couple of my first earlier bells, because I cast the smaller bells first, as they tested the sound inside the space. Can you see that? There's 2 of the bells, 2 of the 10 bells in the clock mechanism. This is me working on the largest bell, which is 500 kilograms, and that's the casting of one of the bells. And this is the bells being packaged up and sent off to San Francisco, where the clock was being put together.
Anton, how deep is that hole that they've dug?
I think it's 500 foot. It's huge. I've not been there. Obviously, I've not been there. Yes. I hope one day to get there. But there is, you'll see YouTube that you can note down and go to, and it tells you the story of the 10,000-year clock, and you get to see how amazing it is, and you get to hear the bells. So if you're interested in the 10,000-year clock, but it was an absolute privilege to be invited to do that work, and this is what a difference tone sounds like. So I'm not sure if you can hear the frequency overtones that are forcing your ear to hear a note an octave below the lowest frequency in the bell itself. So it's a very, very, very beautiful bell, and absolutely wonderful project to be involved in. Let there be more.
Who was funding the...
So Jeff Bezos put $42 million into the project, and they're in the stage of testing the bells now, and nobody knows when they're going to open the bells. But when the clock, not the bells are minor, the clock, and when it's opened, it will be possible for people to visit. But I think you have to walk across a desert. You have to climb a mountain. If you look at that YouTube, you'll be amazed at how hard it is to climb halfway up a mountain. There's a wee little opening. You go through that opening. There's no electricity inside, so you go through. You go on an adventure to go there. Then you can walk the steps up to the top where there's a dome, and the bells ring every day at noon if there's sufficient energy, and the energy is driven by a weight. And at the difference of temperature between night and day at the top of the mountain, an Atmos engine pulls the weight up. And of course, weight is what drives the clock. So if nobody goes there, the clock will keep on going. The bells won't ring if it doesn't have enough energy, but if it does, the bells will ring noon every day, but they'll ring a different pattern. The reason why there are 10 bells is every day for 10,000 years I'll ring a different pattern, in combination, that becomes a possibility. 32,000 something or other possibilities. So if you go there, though, there is a turntable in bronze that you can walk around, turn around, and lift a weight up for the bells. So if you go there, and then you add you add energy, then the bells will ring while you're there. So, and the clock is self-adjusting over the 10,000 year period. It's an engineering absolute wonder. So I recommend you do check that out. And like I say, it was wonderful being invited to design the bell. So the Research Direction's Australian Bell, that's me, is exploring is the musical possibilities of ancient Chinese bells. And I'll just say these and then I'll explain them a little bit more. New shapes and sounds for twisted bells, 3D printing bells in metal, and mechanical clocks and bells as sculpture. So taking them one at a time, researching ancient Chinese bells. Part of the research for the Federation Bells was travelling through Southeast Asia and Asia, North Asia, looking at bell traditions in Korea, in Thailand, in Japan, and in China. And after the revolution in 1949, bells were collected from all over China and brought to a 7-acre monastery on the outskirts of Beijing. And when we got there, it was just amazing to see 500 plus ancient Chinese bells just sitting there. And we were analysing as many of them as we could. And amongst them was a replica set of the Marquis Yi ney bells, or elliptical bells. And there's a picture of them there. So they're replicas of what were the Warring Period grave goods of this set of bells found in China and are too precious to play. But this replica set came out to Australia 2 or so years ago, and I went to the concert of them playing some of those beautiful replica bells. And when we were at the Beijing Bell Museum, we were invited to play those bells. So I got very excited about elliptical bells and what might be possible. And so when I got back, I started casting replicas just to see what the acoustic outcome would be. And bit by bit, I've refined the elliptical bell so that it's got quite a beautiful note. And I have been trying to get an orchestral set of these ancient Chinese bells made musical, so that community players, might do concerts in China, and maybe Chinese players might use these orchestral bells and do concerts around the world. It might be a cultural exchange between Australia and China. It's a possibility that excites me enormously. And these elliptical bells were the very first musical bells made by human beings in the Shang dynasty. So that's 1500 BC. So as a bell maker, one working with these ancient design and trying to use computer technology to bring them to a state of contemporary musical tune makes sense to me, at least. So that's Chinese.
Anton, you've had experience with FEM and the software.
Yeah.
Will it ever be good enough to get reasonably close to these bell tunings that you're trying for, yeah, or will there always be a manual process?
The story with making harmonic bells we were about to go to Japan and to see the casting of a bell, and working with Professor Joseph Thomas at Aeronautical Engineering RMIT, we'd started off with a cylindrical bell, a cylindrical Asian-style bell, which he had made the virtual model, but his software, finite element analysis software Reshape, was unable to resolve a harmonic sound with that shape. And so we had a meeting two days before we got on an aeroplane to go to Japan, and he's going, oh, well, what other shape should I do? And I had a polystyrene coffee cup, and I said, just do the polystyrene coffee cup cone, keep the outside straight, let the computer do whatever it likes on the inside. And when we got back, this is what the computer had generated. So in this case, the computer generated an accurate outcome. In this case, it took a lot of work to refine it. But there's no way one could get there without the software, because it's just too far away from any expectation or understanding. So that's my interest in Asian bells. The other interest I've got is in the twisting of bronze bell shapes. I don't know if any of you have seen the 3-metre tall twisted bell on the Yarra banks of the Yarra River in Stonington. Near Melbourne High School, there's a 3-metre tall twisted bronze bell, which gives a lovely D 74 hertz note, very low droning sound when you strike it by your hand. And I'm really excited with the possibilities of doing really interesting forms and sounds. So I've been playing with that, and I tried to talk my way to represent Australia at the Venice Biennale with the pavilion filled with these amazing cylinders, each one holding a frequency array, so that people would walk through and it'd be like this amazing space of sound that the world would be blown away by. But no, couldn't interest them. But all you can do as an artist is try persuading people. But people are very difficult. You probably know this. People are very difficult to convince, and they have their own head space. I was lucky enough to in 2017 get a Synapse residency at CSIRO, Lab 22 in Clayton, where they research 3D printing. And oh, how did that happen? Why is that having trouble? Does not like the video one little bit. So I'll just do that again, and I don't know. We might be stuck with him cutting out every time because of the video. So maybe I'll just explain that. So this is a difference tone bell that's been 3D printed in titanium, and with the CSIRO, we worked with an American company to also do 3D printed stainless steel difference tone bells, just to explore the possibilities. And I mean, these are the only 3D printed bells that exist in the world, but it is absolutely the future of bell making. And what makes it wonderful is that the computer program generates incredibly complex shapes, and they become quite difficult to cast in traditional casting. Even being clever with how you make moulds, there are limits to pouring liquid bronze or liquid stainless steel or liquid metal of any sort. But those problems don't exist with 3D printed metal. And so it's clear that the future is going to be new, exciting, amazing shapes and sounds generated with 3D printing. I've tried to persuade boat owners that there's a digital yacht designer in New York that I keep sending emails to saying, your bells really should be 3D printed, without getting any sort of response. But I'm convinced that this is the future. CSIRO Lab 22 are being very nice to me. They've got a robotic arm, a laser 3D printer using stainless steel wire, and they're printing a harmonic bell, one of these bells, for me, and I'm hoping I can beam print in titanium some harmonic bells as well. So that's just part of my research to keep keep that possibility expanding, because the minute I stop, the rest of the world will come running in, because it's obvious that that's the future of bells, of music, of we could build an industry of musical instruments that are all 3D printed. You can see how far gone I've become. I have to avoid that slide.
How long does the 3D printer take to print that?
Oh, that would be something in the order of 5 days. They do take a long time because it's so many revolutions, and it's made out of a box of powdered titanium, and the box drops down as it fuses the next layer. So it is a slow process, and it's expensive. I don't know how I'm going to get. Oh yeah, I know. I'll just see if I can go straight past it. Oh, did I? Well, there's the twisted bell I was telling you about. That's 3 meters tall. Keep going. Right, and the design and making of clocks. So, inspired by the 10,000 year clock, I thought when COVID struck, I thought, I don't know anything about clocks. I should find out about clocks. And because I'm using software to design bells, that same software is perfect for laser cutting, metal. And so I've had, for the last, 5 years, extraordinary fun designing strange clock objects that ring bells, trying to make the bell the major part and the clock the minor part, the servant to the bell. And so doing the design work, making a 3D model, and then sending off the DXF files for the laser cutters, and then going and picking up a box of bits, and then tapping and using bearings and putting it all together. Boys own Meccano. It's just too much fun. It should be illegal. So the one clock I've got in public is at Romsey Ecotherapy Park, and that's that picture of that there. And so there's a bell inside that mechanism, and there's a movement sensor on the water. So when you walk into that area, the water flows into that landscape. I don't know if you can see, but that's a little island in an ocean, and so you get a sense of this little island with a little lighthouse in an ocean, and the water drains, excess water drains and fills up the little cups and turns the wheel that turns the gears inside, that after a period turns more gears, that finally rings a bell. And when this opened, little kids were spinning it like crazy, and I'm going, oh, no, get your hands off it. This is a contemplative work where you sit there and you just take it in, and then the bell strikes. No, so kids are very enthusiastically spinning the wheels. So that's my little talk to you. That's where I am, if any of you are interested. You can see in Darwin, if you go to Darwin in Chinatown, there's a little poncho bell structure holding an octave of ney bells. That's the one in the middle, Darwin. Yeah, that's it, Darwin. And and there are a bit of my clock bits and pieces. So you can see I'm having a lot of fun. I'm sorry if I've bored the hell out of you guys, but it's always fun to come and talk to you about it. And so this is a harmonic bell. So it's a bell with a beautiful sustain, beautiful single clear note, and there's a large bell in a stainless frame being installed very shortly in Kingston, in the beauty spot, a little park where the Patterson River comes out into the bay. So if you're driving by there, mid-July, you should be able to go and strike that harmonic bell, and that's at 138.6 hertz, which is reputed to be the Om frequency. So you can go and get healed. I'm not guaranteeing that. You can go and feel peace. I'm not guaranteeing that either. You can go in there and have joy, and you can go there with your friends and share creatively, playfulness together. So with my public art, I try and persuade councils that I think public art in the 21st century shouldn't be statues, shouldn't be sculpture that's abstract, that means little to most and a lot to a few. It should be places that bring the community together in creative shared play. And music is one beautiful way, not the only way. Other architectures might exist where people can play creatively with each other, but music is a beautiful way for people to come together and to share their creative imaginations with one another. And in the sort of society with the challenges we have, the sort of the connectivity we need public art that brings people together. So that's the spiel I give to people. Here's a little 3D print of that. So all of my bells are 3D printed and cast using 3D prints. I'm happy to answer any questions.
So Anton, that is the tool that you'd use to make the mould?
Yeah, that's the pattern.
Yes.
So the bells all exist as 3D prints in plastic. Of course, not in this case because it's the actual 3D print itself. And then, the resin sand on the inside, resin sand on the outside, pull apart, take it out, put the moulds together. The negative space is filled with bronze. And Bob's your uncle. So they're all designed in computer virtual space and then made, the 3D printers print the patterns. My place is full of 3D printed patterns and bells. Because all of my work is experimental. So I see myself as trying to push frontiers at every point that I possibly can.
And this is your workshop at home?
Yes, my workshop is the messiest place in the world, but I love it. Oh, okay, you and I will share the broken down cup. My son just wants me to clear the 35 years of working in the one space, just generating things. The clocks are starting to close in on me now, but then I had a big breakthrough yesterday on a little mechanism. I thought, would that work? And in the computer model I made, it worked. And then yesterday I put the actual bits together and it worked. And do I feel happy and proud? I shouldn't have hit that. Sorry about that. So that sort of level of excitement is what keeps my juices flowing.
Where do you source all your material from?
The bronze. Okay, so I work with Castlemaine, Billman's foundry in Castlemaine, and so even though I've got a foundry at home and a number of the Federation bells were cast where I live, and we had employed people working there, it's just me by myself, it's pointless being endangering myself with large volumes of metal. 400 kilograms of liquid metal, bronze, is a problem if it spills. So I cast small things for myself, but I work with a foundry in Castlemaine and have done for the last 25 years. So I go and make the molds or give them the 3D prints. They do the work, they cast it, then I take the bronze home and then I tune it and then send it off to wherever it's got to go in the world.
Anton, is that process used with the 3D print for those twisted bells? Because I can't imagine how you pull that piece out.
No, okay, so first of all, they're made as 3D prints, okay. And I could have brought one along. I should have maybe brought a little 3D. They're beautiful things in themselves. But then once I was commissioned to do the work, I worked with C5 a milling place in Clayton. They mill polystyrene. So they take that pattern and they break it up into foundry segments that a foundry can lift a pattern off, and they mill polystyrene segments. So I've got all those segments in polystyrene at home that was used in Billman's foundry to make each panel, and then the panels are all welded together. So, and similarly with that tall tubular bell, which is, will be reinstalled in Brunswick at the Brunswick Library on the 19th of this month, which I think must be soon. And that's a 3 metre tall tubular bell, but with a twist in it. And that also has a really beautiful note. So yeah.
Do you tune those too? You give them a tuning?
No, they can't really tune them because having cast one, it's possible now, because I know the frequency of that, to do calculations to, by how much it should shrink. Yeah, but I couldn't work out beforehand because the shape's too complicated. So yeah, like Asian bells aren't tuned either. No Asian bell is tuned musically. These twist bells aren't really tuned for musical outcome. They're tuned for making interesting sound. There's one I've got that I'm in proposal now for Dandenong, which has got a skirt. It's like a skirt floating. And in the little sample I cast myself, you strike this part and you get one note, you strike that part, you get another note, strike that part, you get another note. So I'm really hoping Dandenong City Council goes for this sculpture in front of the Drum Theatre so that I can see if that's going to be true for one at 1.5 metres high.
Okay, well, we're far open to questions, I think. There's a lot of questions, so there's one at the back there first.
There's a program that I've used before for other things that might be applicable here called COMSOL, C-O-M-S-O-L.
Oh, I don't know it.
It's a multi-physics program, so you can model anything and combine different things. So it strikes me, no pun intended, that you could use something like that to both make a complicated shape and model the pitch.
That's probably true. I'm working with Aplodyne in Adelaide, and it's very expensive to work with them because of the time it takes for them to employ somebody, one of their employees, to do the work. Kindly, they're doing some work gratis, just as a measure of support, and so the quid pro quo will come if I get commissioned to do a project. Then I work with them and pay them, and then we will have a go at doing very complicated shapes. And they've got some finite element analysis software that they're really interested in exploring. So there are a range of different programs out there, but they're all very expensive to access. And
Console's expensive if you buy it all, but there's a base.
But even just to and the other side is, I haven't got years enough to learn that software package, and so it would be foolish for me to do that when there are people who are capable of using those packages. I use what resources I have to keep them interested. Similarly with the 3D printing of metal, they're doing work gratis, and I'm grateful. And again, if I can score a commission, then I can kind of pay back then. But I don't have huge amount of resources. After all, I'm an artist, and so poverty is something I've accepted as the way forward. Nevertheless, whatever income I get, I put into research, because it's the most important thing that I can think there is. And I've been lucky enough to get public artworks that have supported my research as well. But keeping those connections up with the people who can do the things that I can't do, and keeping them interested in what I'm interested in, that's a minor art form. I hope none of them are listening, in case they lose interest. What?
Who holds the microphone has the question.
Anton, could you please explain how you tune a bell?
Okay, so theoretically, a bell, has a series of frequencies given by the profile, and if you've cast the bell well, and there's no porosity in the bell, so the bell's got a constant density, then the casting will have a sound, the sound of those existing frequencies. It's possible to push frequencies apart and together. Some frequencies link to each other, so you push that one down and the other one goes down. So it's not simple to be able to push frequencies apart or together. So you typically take metal off. Now, I can add metal because I use silicon bronze. Bell metal, you can't weld. Or you can't weld successfully. So bell metal is 80% copper, 20% tin. So bell metal bells, traditional bells, simply have to have metal taken off. And actually, when they cast an English bell or a European bell, they're way too thick. And they put them on a lathe, and because the outside often has text and decoration, they have a vertical lathe, and so the bell sits up like this, and the lathe cuts the inside of the bell, and you've got an electronic equipment, so that you ring the bell, it does an analysis of where the frequencies are, and you decide, I'll take more off there, less, take some off there, and they're fairly crudely done. So the world I inhabit is to do all the work in the virtual space. So I do all the design work, I've cast samples, I know with this bell its frequencies and its note, I know its scale, it's in the computer, then I can do all the work in the computer and make a 3D print, and I know that it will come out on pitch with the right frequency. A bell is tuned not only at the pitch, which is the easy part because a note is 1/12 of an octave. So it's a simple mathematical function. If I take this bell and double it exactly, it will be exactly an octave lower. If I make this bell exactly half again in size, it will be exactly an octave higher. So it's very mathematically easy to do pitch. Really, really difficult to get profile so that those 5 lowest partial frequencies are in an array that satisfy your ear.
Okay, we've got a question online from Aura. Hi, can you elaborate on the effect that different materials have in the bells? A related question.
Sure. So it's really interesting. If the profile's exactly the same, the frequencies are going to be the same. But what's different is the duration, how long it will ring for. This bell will not ring anywhere as long as the bronze one, the 3D printed one. So they've got the same profile, but the bronze is much longer to find equilibrium. So the material is just about duration, as far as I can make out, because the frequencies are the same.
And a supplementary question. Have you thought about combining multiple materials, for example, in layers?
Wow. I've had discussions about that. You'd have to convince yourself, because technically that's quite a complicated thing to do. You'd have to really make yourself understand what you were hoping to get out of that. So the answer, I guess, is no. But, people have said, oh, what about... When I first was working on the difference tone bell, I was thinking to myself, well, even if I can't resolve it, perhaps I could have two bells within a larger bell and a smaller internal bell, just like an organ pipe. And if I can ring them simultaneously, I can get a difference tone that way. So that would be my fallback position. So that's the kind of putting in multiples into a single. Whether that'd be different materials, that could be a solution. For example, aluminium has a beautiful sound to it. A bronze aluminium combination could be quite really lovely. Internal, external. So it's a possibility, but maybe that person's going to have to beat me to it.
Well, they might get in touch with you.
Yeah.
Also, have you got your favourite alloy?
Oh, I love silicon. I love silicon bronze. It was invented by the Americans in the Second World War. Kuselman bronze, silicon bronze. It's 94% copper, 1% manganese, and 4% silica glass. So it is an absolutely amazing. They invented it because brass and LG bronzes, leaded gun metal bronzes on their warships corroded really quickly in the ocean, and so they were trying to find a bronze that wouldn't corrode as fast, and so they invented Kuselman bronze. And when I was in the 70s working in a foundry, 70s, 80s, early 80s, all of our castings were in leaded gunmetal bronzes, which you couldn't weld very well, and so the figures had to have Roman joints with stainless steel pins, and they're welded over the top because the welding couldn't support somebody hanging off it, and then silicon bronze came through the sculpture foundry industry, where you just cast, or you cast an arm, weld it, and it's as strong, you could hang people off it. It's strong. So this amazingly wonderful metal is very weldable. The manganese stops the heat from running away like it does on copper. So on copper, if you try and weld, well, all the heat runs away from the weld site. The manganese inhibits that, and so it makes it beautiful to weld. It's a beautiful casting material, and it's perfect for bells. And all the computer models are done in silicon bronze. So that's part of the programming. What metal do you want your virtual model to be done in?
Thank you.
I'm amazed I haven't brought out the boredom yet.
I would like to bring you back to the orchestral bells. You mentioned that you have 12 bells for an octave, so it's
Yes.
a complete octave like a piano
Yeah.
keyboard.
Yeah.
How many octaves have you seen made, and how many do you make for your?
Well, I think the world's largest carillon in Columbia, New York City, the Rockefeller Church has 73 bells, and that's 7, 8 octaves perhaps. The Sydney Opera House has 73, I'm told, small bells, the smallest being quite small, that came with the organ in the 1960s, I believe. They're all flat. They're flat, and they've been trying to work out how to tune them. So, that's a large set of bells. 63 for Marcus Yee. The Federation Bells has 39 bells.
So it's a full piano keyboard, effectively.
Well, piano keyboard's 88 keys, so it goes from really low to, those top keys. When you can probably tell the difference, I can't. I mean, they're just, So, but the problem with bells is that when you've got a carillon, you've got very large bells for the low notes, quite small bells for the high notes, all mixed together. And so it's very hard for those high notes to be heard with the depth of sound in the low notes. And so bell foundries typically make the high note bells, the smaller bells, quite thick, so that they can generate a sound that you can hear. But it's a less satisfactory sound than the better tuned lower note bells.
Can I ask, I notice you strike the bells with a little hammer there.
Yeah.
It's different materials you use to strike the bells. Does that create a difference?
Yeah.
I mean, the big Japanese bell, they usually use some...
They use wood, wood. And it makes a big difference. So this is a rubber, and if I hit the harmonic bell again, I can get it to resonate without that strike note. And so you just get the pure sound, as opposed to... You see, the harder it's hit, if you hit a bell with cast iron like European bells are, it brings out all the upper frequencies that are chaotic, but they're up in a tower, and by the time it gets to your ear, all those upper frequencies have been exhausted. They don't last very long, milliseconds, and then you get to hear the basic fundamental frequency of the bell.
Okay,
Done?
we have another online question from Aura. Good questions. I think the question is, can you control reverberation lengths for different partial tones?
The sound wave is going to be longer the lower the pitch, but the thing is, in a bell, they're all locked together. So none of them are free flowing or free to do what they'd like to do. They're in lockstep with each other, and so the weakest frequency is going to dominate, the more long-lasting one. So no, I don't think you can control that. You can just control the frequency array, the relationship between the partial frequencies. And then you're stuck with what the cumulative outcome will be of those 5 or 6 frequencies.
Okay, you probably could make it so the bell decayed more quickly at high frequencies, but that would only mean that overtones detect.
Well, that would be a thicker bell,
Yeah.
and then it would just, die straight away, ish.
And Nuttalex asked, does a 3D printed metal bell behave differently to a liquid cast bell of the same metal?
Well, I've not cast a titanium difference tone bell, so I don't know. I would think the frequencies would be the same, but the duration would be different because the density would be different. This 3D printing of particles has got to be a different density than liquid titanium poured into a mould. And so I would think the liquid titanium would be denser, and therefore I would think it would have a longer lasting duration. That would be my guess. I've not done it.
Okay, thanks you very much for that. Any more questions?
You are very good as an audience. Thank you.
Is it true that the Liberty Bell in Boston has got a crack in it?
It's got a crack. Yeah. My understanding is it came out from, was it Whitechapel? I think Whitechapel cast it originally. It cracked. The Americans melted it down again, recast it using the same metal, cracked again. And then they, if I've got this right, they melted it down again, recast it using the same metal. It's cracked again, and they're just leaving it. The Big Ben's got a crack in it. That happened 2 months after it was installed. And then the solution was to halve the clapper. In Big Ben's case, it's a hammer, an external striker. They halve the weight of the hammer, and it's managed to not have that crack proceed all the way through. Bell metal has so much tin in it that it's brittle, very brittle. If I had a European bell standing on a concrete floor, I dropped it, it would break and break. And I've seen in a bell foundry in Europe them using a sledgehammer on a large bell that miscast, and it breaks like eggshell. You'd think it'd be resistant, just cracks. There's so much tin in it in order to get that resonance and that duration that it's really at the edge of what's possible. 23% tin. I did some experiments with trying to put the tin as high as possible, and the little samples I cast break like glass. They're like glass. So there are real physical limits with the metallurgy of bell metal, which is why silicon bronze is just such a wonderful revelation, although to European bell makers it's sacrilegious. It's in fact most of what I do is outside the realm of their imagination. So
okay, there's one more question here.
Temperature change.
Big difference. So
a freezing cold day or a very hot day.
Very big difference. And when I did a set of bells for the city of Darwin, not the Chinese ones, but a large set of bells in Civic Square, if you're in Darwin, I had to calculate because I'd been up there, and it's so hot you can't put your hands on the bronze bells, and it would lift the note by, it would drop the note if it was hot by 10%. So I had to make them all sharp to try and calculate midday versus in the evening, because the notes are going to be quite different between those periods. So it's a wee little bit tricky when I'm, that's why a bell in a tower, is great, because it's protected from the weather and from the sun.
You're just doing this so I can get to you.
Sorry?
Lots of questions.
Yeah.
Hi, Anton. Thanks for the presentation. It's
Pleasure.
absolutely amazing. Coming back to the temperatures, do you find like over time with the constant temperature changing and whatnot with bells and that, do they eventually after a while change their tonal properties and whatnot?
They do, and Japanese bells, they're struck by a large piece of wood. Big bells, like 40-ton bells, like the Chion-in bell in Kyoto, which is huge, this thick, maybe 4.5 metres tall. It's struck by a tree trunk. But at the Japanese bell foundry, we were there to watch a 1-ton bell being cast for a distant Japanese community who were there all dressed up with their Shinto priest, ringing a small bell as the metal was being poured and chanting and throwing food into the metal. What? Anyway, the reason why that village or that community had to get a new bell is their old bell had become elliptical because it just bit by bit being hit on the one spot goes from being round to elliptical and loses its note. And so in the 10,000 year clock, I insisted that my bells are on bearings and they turn. So over 10,000 years, they're not struck in the one place, that they're constantly worn evenly so that they don't slowly become elliptical.
Questions? No. Okay. Well,
Oh,
I really want to thank you, Anton.
thank you,
For
Graham.
what I think you'll all agree was a fascinating talk. I'm thinking that some of the speaker cones
Oh, yes,
could be bells.
they could. They were
So
vibrating.
that's something for the audio guys to work with.
Yeah.
Thank you very much for coming
My
along.
pleasure.
Most informative. We'll have details of how to get in touch with Anton available, and you'll make the slides available if you can.
Yeah, sure.
And here's a little token.
Thank you so
of
much.
esteem
Thank you.
from us.
Oh, wow.
Tonight.